All right, welcome. If you've got an atmospheric science exam coming up, then you've come to the right place. Think of this as your ultimate review session. We're about to take a really deep dive into the invisible forces that basically choreograph our weather. Everything from a gentle breeze to a full-blown typhoon. So take a look at this. You see the swirling clouds, this massive storm system. But what is really going on in there? Well, it's not just random chaos, It's this beautiful, elegant battle between powerful, invisible forces. And the big question for any meteorologist is always, what forces are running the show, and how can we use that knowledge to predict what it's going to do next?
To get to that answer, we've got to start with the absolute fundamentals. At the heart of any typhoon, or really any weather for that matter, is the one concept that gives it life: atmospheric motion.
Okay, so the most important thing to get is that nature just hates imbalance, right? So whenever there's a difference in pressure or temperature or even density, the atmosphere is going to move air around to try and even things out. That movement, both side to side and up and down, is literally what we experience as weather.
All right, let's get into the core of your review, the 4 key players that control horizontal motion. We're talking about the wind you can actually feel blowing on your face. First up is the main engine, the prime mover, the pressure gradient force. We just call it PGF. Think of this as what gets the wind started in the first place. It's the most basic rule there is. Air will always, always try to move from a crowded, high-pressure zone to a less crowded, low-pressure zone. And the bigger that pressure difference, the stronger the push, and the faster the wind. Simple as that. Next, we have the Coriolis force, and this is the one that always seems a little tricky. But the single most important thing to remember is that it's an apparent force, okay? It's not really pushing the air. It just looks like it is because our planet is constantly spinning underneath it. So here's a great way to picture this for your exam. Imagine you're on a spinning merry-go-round, right? And you try to throw a ball straight across to your friend. From your perspective, it's going to look like the ball curves away, but the ball is actually going straight. It's the merry-go-round that's turning under it. Well, the Earth is our giant merry-go-round, and the wind is the ball. The wind wants to go straight, but the Earth's rotation makes its path look curved. And this leads to 2 absolutely rock-solid rules you have to know for your exam. Deflection is always to the right in the Northern Hemisphere, which of course includes the Philippines, and it's always to the left in the Southern Hemisphere. You gotta lock that in your memory. It's a classic exam question for a reason. And finally, we've got the 2 supporting actors. Friction is pretty much what it sounds like. It's the drag from the Earth's surface. Think mountains, trees, even buildings that just slow the wind down. Then there's centrifugal force. You know that feeling that flings you outward on a roller coaster loop? That's it. It only really becomes a factor when the wind is already moving in a curve. So how do these 4 forces actually work together? Well, let's see how they create that signature spin of a tropical cyclone, or, as we call it in the Philippines, a bagyo.
This diagram shows it all perfectly. It's a dynamic balancing act. So in a typhoon, which is just a really intense low-pressure system, the PGF is desperately trying to pull air straight into the center. But the Coriolis force keeps deflecting that moving air to the right. And what do you get? You get that classic counterclockwise spiral. That is the signature spin of a typhoon right there.
This balance is absolutely everything. If that low-pressure center gets even stronger, the PGF ramps up, pulling in more air, and boom, the storm intensifies. But if the storm moves over land, friction suddenly gets way stronger, slowing everything down and messing up that balance. This constant tug-of-war is what determines if a storm fizzles out or grows into a monster super typhoon. Okay, let's zoom out for a second. This very same battle of forces doesn't just make individual storms. It actually dictates entire climate patterns. And this is how we get the things that really define the Philippine climate, like our famous monsoon seasons. Oh, this is a fantastic comparison. Look, on the left you see the forces at work in a single storm. But on the right, you're seeing the exact same principles playing out on a massive planetary scale. These huge circulation patterns, like the Hadley cells you see here, are really just giant versions of the same process. They create the predictable wind belts that shape our entire global climate. Now, for your exam, this is a really important distinction to make. General circulation, that's the perfect, idealized 3-cell model you see in textbooks.
But large-scale circulation is the messy, dynamic, real-world system. And that system is the reason the Philippines gets its distinct wet season with the Habagat, the southwest monsoon, and then the cooler, drier season with the Amihan, the northeast monsoon. So let's pull all of this together. Why does knowing all this stuff matter beyond just passing your exam? Well, because in a country like the Philippines, understanding this invisible balance literally saves lives.
And here's where the rubber meets the road. Meteorologists at Pagasa feed all the data on PGF, Coriolis, friction into these super powerful computer models. These models calculate the shifting balance of forces second by second, and that is what allows them to predict a typhoon's path and its intensity. This is the hard science behind every single storm warning you ever see. And really, that's what this is all about, isn't it? It's about making the invisible visible. It's about turning abstract physics into real, tangible, practical predictions that allow our communities to prepare for what's coming.
So as you're studying, here's a final thought to chew on. A warmer world means there's more energy, more fuel in the atmosphere. And that extra energy could supercharge the pressure gradient force, completely changing the delicate balance we've been talking about. What that could mean for the future of typhoons here? Well, that's one of the most urgent and important questions in atmospheric science today. Good luck with that exam.